Hi everyone. Back at the beginning of the quarter, we talked about a term called statistical inference. We said that statistical inference is using data from a sample to reach an unproven conclusion about a population. It's called an inference because you can't prove anything about a population with data from a sample. In the last couple of videos, we've been talking about a certain type of statistical inference, which is using the mean of a sample to estimate the mean of a population. That's really one of the most basic types of statistical inference. And we've been covering some of the technical details of using a sample mean to estimate a population mean. For example, we talked about how a value called the standard error and another value called the margin of error can be calculated to show how accurate the sample mean is likely to be. If the standard error and the margin of error are both small, then the sample mean is likely to be accurate. The sample mean is likely to fall near the population mean. If the standard error and the margin of error are large, then the sample mean is likely to be less accurate. It's likely to fall further from the population mean. And we talked about how the standard error is affected by the sample size and the amount of dispersion in the population. If the dispersion in the population is high, or the sample size is small, the standard error is likely to be larger, and the sample mean is likely to be less accurate. If the population has less dispersion, meaning the population members are more similar to each other, or the sample size is large, then the standard error will be small, and the sample mean will be more accurate. And the margin of error is directly connected with the standard error, so when the standard error goes up, the margin of error goes up along with it. We'll talk a little bit more about the standard error and the margin of error in this video. In the last two videos, we've also been talking about something called the central limit theorem. And the central limit theorem says that if you want to use a sample mean to estimate a population mean, either the population that you're sampling from needs to follow a normal curve, or your sample size needs to be at least 30. One of those two things needs to be correct, or true, because if one of those two things is true, then the sampling distribution of all possible sample means is normal, and the margin of error can be calculated. The margin of error can only be calculated if the sampling distribution is normal. That's why it's important to either be studying a normal population or to have a sample size of at least 30. And typically, in a lot of studies, you don't know if the population is normal. That's because you don't have data from the entire population. That's why it's usually safe to always use a sample size of at least 30 when you're using a sample mean to estimate a population mean. In the last couple of videos, we've been talking about how the standard error and the margin of error are calculated when the population standard deviation, sigma, is known, when the researcher knows what it equals and can plug it into the formula. In most, or in all studies in which a researcher is using a sample mean to estimate a population mean, the researcher actually doesn't know what the population standard deviation equals. And the researcher has to use slightly different formulas to calculate the standard error and the margin of error. And we'll actually talk about those formulas in this video. In this video, we're going to talk about how the standard error and the margin of error are calculated when the population standard deviation isn't known. And like I said, it's pretty much never known in any study because the only way you can calculate the population standard deviation is by having data from all members of the population. So here's a made-up data set. These are the 30 sleep times of a sample of 30 people. These are each person's answer. So here's a person who sleeps 4 hours per night. Here's a person who sleeps 3 hours per night. And here's a person who sleeps 2 hours per night. I recorded their 30 answers by doing a survey. And let's say that this is a random sample. This sample of 30 people was randomly selected from the population that they came from. I said that it's important for the population to be normal, or the sample size to be at least 30 when you're using a sample mean to estimate a population mean. It's actually also important for the sample to be random. If the sample isn't random, the standard error and the margin of error don't mean anything. So we're going to definitely say that this is a random sample. So now we're going to go through the steps of calculating the standard error and the margin of error without knowing what the population standard deviation equals. And when the population standard deviation is unknown, the standard error that the researcher calculates is actually called an estimated standard error. It's not the true standard error. It's actually just an estimate of what the standard error equals. And in one of the earlier videos, we talked about how the standard error can be calculated with a short formula when the sample size is a lot smaller than the population size. The short formula can be used when the population is at least 20 times bigger than the sample. And that short formula was this formula right here. The population standard deviation over the square root of the sample size. The formula for the estimated standard error is the same as the formula for the actual standard error. It's just the population standard deviation is replaced with the standard deviation of the sample. And the sample standard deviation is the letter S. So the formula for estimated standard error is S over square root of n. To get the estimated standard error, you calculate the standard deviation of your sample, and you divide that by the square root of your sample size. And since the sample standard deviation estimates the population standard deviation, this estimated standard error estimates the actual standard error. This whole thing estimates this whole thing. And if the population is at least 20 times larger than the sample, then I can still use a short formula like over here. The only difference is the standard deviation is the sample standard deviation and not the population standard deviation. So I'm going to say that the population is 20 times bigger than my sample, and I can use a short formula. So we're going to go through the steps of calculating the estimated standard error. First, we have to get the sample standard deviation, and we're going to do that with Excel. I'm not going to enter all of these numbers into Excel right now. So I've entered all of my numbers into Excel right here. These are the 30 sleep times from my random sample of 30 people. I can calculate the sample standard deviation by typing in equals stdev point s. And then entering a left parentheses. The point s stands for sample. If it was population, it would be point p. Now I highlight the 30 numbers, or I can just type in A1 colon A30, and it'll calculate the standard deviation of all numbers between A1 and A30. So this is saying it's going to calculate the sample standard deviation of all numbers between A1 and A30, which is my entire data set. Now I press enter, and it gives me the number I'm looking for, the sample standard deviation. Remember that when you're calculating a sample standard deviation, you use n-1 in the formula. So Excel used the n-1 formula to calculate the sample standard deviation. Now I'm going to copy this number and move it over to Paint so I can use it in the formula. I'll see if I can blow it out. It's a little bit distorted, but it's okay. So I need to divide my sample standard deviation, which I calculated with these 30 answers, by the square root of my sample size. My sample size is 30, so I'm going to divide it by the square root of 30. I'll bring up my calculator right now. So what I can do is I can type in a scientific calculator, I can type in 2.116167, then the slash for divide, and then type in the sample size, 30, and then hit the square root key. It's right here. And it'll divide standard deviation by the square root of 30. And it already gave me my answer. So this is our estimated standard error. This is the value that we calculated to tell us how far the sample mean was likely to fall from the population mean. So let's see if I can paste this in here. It's not letting me paste, so I'll just round off the answer. It's about 5.48 if I use 2 decimal places. So our sample mean, so the mean of this sample, or the average of this sample, is likely to be about 5.48 away from the population mean. The mean of this sample is likely to be about 5.48 off target in estimating the mean of the entire population. I still don't know what the mean of this sample is. To calculate it, I would just add these 30 numbers and divide the total by 30. So I can actually do that with Excel also. This was the sample standard deviation. I'll just go one cell higher, and I'll type in equals average A1 colon A30, and then close the parentheses and press enter. Excel uses the word average for mean, but average and mean are the same thing. So now I have the average of all 30 answers, and it's 5.73 if I round. Remember that the symbol for sample mean is X bar. So X bar is 5.73. 5.73 is the average of all 30 sleep times. So what this estimated standard error is saying is that this sample mean was likely to fall about 5.48 from the mean of the entire population. So we can expect the population mean to be anywhere between maybe 0 and 11, maybe, because this sample mean is likely to be about this far off target. But one thing we have to remember is that this actually isn't the true standard error. It's an estimate of the standard error. So the standard error, or the standard error, which is the amount that this sample mean is likely to be off target by, is roughly this number, because this is just an estimate of the standard error. But with a decent sample size, the estimated standard error is pretty close to the true standard error. It isn't off by very much. Now let's calculate something called the estimated margin of error. When the population standard deviation is unknown, the margin of error has to be estimated, just like how the standard error has to be estimated. And remember that the formula for the margin of error is multiplying a value called the confidence coefficient, which comes from a table, by the standard error. The same thing is true about the estimated margin of error. You just multiply the confidence coefficient by the standard error. But when you're calculating an estimated margin of error, the symbol for the confidence coefficient actually isn't z. It's a different symbol, which is t. So when the population standard deviation is unknown and you're calculating an estimated margin of error, the symbol for the confidence coefficient is t instead of z. So it's t times our estimated standard error. That's the formula for the estimated margin of error. It's t times estimated standard error. We already know what the estimated standard error is. It was this number right here. So we can plug that in over here. We just have to know what t equals. And to find t, you have to go to a table called a t table, and I'll show you how to use that table right now. Here's the t table that we'll use to look up our confidence coefficient. We have to find out the row and column that we need to use. A t table actually has rows and columns. So down here we have to choose something called the confidence level. The confidence level is just the percentage that goes along with the margin of error. So the 60% margin of error has a 60% confidence level. The 70% margin of error has a 70% confidence level, and the 95% margin of error has a 95% confidence level. In almost all studies that calculate a margin of error, the 95% margin of error is calculated. So we'll calculate the 95% margin of error, since that's what's calculated in almost every study that uses a margin of error. So we have to go to 95% right here, and we just have to look at the correct row that we need to use. And I'll explain what these row numbers mean over here. The title of this column right here is DF. I need to explain what DF means. DF is just the n-1 that's used in the sample standard deviation formula. The n-1 on the bottom of the formula for the sample standard deviation is called df. So df is n minus 1. It's 1 less than the sample size. So it's really just a technical name for the bottom of the standard error formula. I'm sorry, I didn't say that right. It's the technical name. It's the technical name for the bottom of the sample standard deviation formula. So it's 1 less than the sample size. Our sample size is 30. 30 minus 1 equals 29. So our df is 29. That's actually the number that we'll need for to look up the row. So we need to go to row 29 because our df is 29. And we'll go to 95% because we're calculating the 95% margin of error. The number that we need is 2.045 because that's where the row and column meet up with each other. That's our confidence coefficient. So t is 2.045. And we're going to multiply that by our estimated standard error, which was this entire thing right here. We already know that this part equals 5.48, roughly. So we could just carry this over here, but maybe if we want to be a little bit more accurate, we could actually put the whole number in here, or at least a few more digits. So maybe we'll put 5.4772. So we're going to multiply these two numbers. And it comes out to about 11.17 if we round. So that's our 95% margin of error. And let's review what the margin of error means. The margin of error shows the range that the sample mean is likely to fall in around the population mean, which is mu. So the there's a range right here that the sample mean has a 95% chance of falling into. So the sample mean has a 95% chance of falling somewhere in this area around the population mean. It only has a 2.5% chance of landing out here and a 2.5% chance of landing out here. The 95% margin of error is actually the distance from the population mean to each boundary of this area that the sample mean has a 95% chance of falling in. So this is the 95% margin of error, and this is also the 95% margin of error. So basically, what we know is that when I took this random sample from the population, my sample mean had a 95% chance of falling somewhere in this area right here. And the um, the 95% margin of error is the distance from the population mean that I'm estimating to the lower boundary of that area, and the distance from the population mean to the upper boundary of that area. So if we replace this right here with this number down here, which is what the 95% margin of error came out to, we'll see that the lower boundary of the area is 11.75 below the population mean, and the upper boundary of the area is 11.75 above the population mean. So what this 95% margin of error is telling me is that when I took this random sample from the population, I had a 95% chance of getting a sample mean somewhere between 11.75 under the population mean right here and 11.75 above the population mean up here. The lower boundary is 11.75 below the population mean, and the upper boundary is 11.75 above the population mean. And I had a 95% chance of getting a sample mean between these two boundaries. So I can be 95% confident or 95% sure that my sample mean right here is somewhere within 11.75 of the population mean that I'm trying to estimate. So that's what the 95% margin of error tells me. I'll say it one more time just to make sure that it's clear. What this 95% margin of error of 11.17 is telling me is that when I randomly selected my sample of 30 people from this population, I had a 95% chance of getting a sample mean somewhere between 11.75 under the population mean and 11.75 above the population mean. This is 11.75 below. This is 11.75 above. And I had a 95% chance of getting a sample mean between these two boundary points. Now, my sample mean wasn't guaranteed to fall between these two boundary points because I had a 2.5% chance of getting a sample mean out here and a 2.5% chance of getting a sample mean out here. But I can at least feel some assurance because I know that I had a 95% chance of landing in here. What this 95% margin of error also tells me is that if I repeated this study over and over again, and I kept on using the same sample size of 30 over and over, and I kept calculating the mean of each sample, 95% of the time I would get a sample mean between these two boundaries. Only 2.5% of the time would I get a sample mean out here, and only 2.5% of the time would I get a sample mean out here. Which is good because I wouldn't want to underestimate down here very often, and I wouldn't want to overestimate way out here very often. I would want to land in this area I would want to land in this area where I get a pretty accurate sample mean. So now we've covered what the estimated standard error is and the estimated margin of error. One thing I want to mention is that just like how this is an estimate of the standard error, this is only an estimate of the margin of error. It's actually technically not the true margin of error So all I can, so all I know is that the true margin of error is somewhere around this number. But with a decent sample size, the estimated margin of error is pretty close to the true margin of error. So number is probably good enough. So I'll recap some of the things we just talked about. If you want to use a sample mean to estimate a population mean, there are a few things that need to be true. You need to be using data from a random sample, and your either the population has to be normal or your sample size has to be at least 30. Because if one of those two things is true, the sampling distribution is normal, and the margin of error can be calculated. So we're assuming that I do have a sample size of at least 30. Well, I'm sorry, I didn't say that right. So let's recap some of the things we just talked about. I said that when you use a sample mean to estimate a population mean, the sample has to be random, and either the population has to be normal, or the sample size has to be at least 30. One of those two things has to be true, because if one of those two things is true, the sampling distribution of all possible sample means is normal, and the margin of error can be calculated. We're saying that this is a random sample, and we can see that my sample size is at least 30. So I've met both of those two things that I need to meet in order to use a sample mean to estimate a population mean. I have a random sample, and I have a sample size of at least 30, which means I'm safe. I can use my sample mean to estimate the population mean. We also covered how in a study in which the population standard deviation is unknown, which is almost always the case in an actual study, you have to calculate an estimated standard error and an estimated margin of error instead of the true standard error or the true margin of error. And the estimated standard error has the sample standard deviation instead of the population standard deviation. And the shortened formula can be used for the estimated standard error, like I did here, as long as the population is 20 times bigger than the sample. And in any realistic study, the population is pretty much always 20 times larger than the sample. If the population wasn't 20 times larger, I would just have to add on the extra part to this formula. The estimated margin of error is the letter T times the estimated standard error. And the estimated standard error is an estimate of the true standard error, which tells you how far off target the sample mean is likely to be from the population mean. And the estimated margin of error is an estimate of the margin of error. It's an estimate of how far these two boundaries are from the population mean on both sides. So now we've covered how these values are calculated and how they're interpreted in an actual study in which the population standard deviation is unknown. Before the end of this video, I wanted to talk about how in some studies, instead of using a sample mean to estimate a population mean, you use a sample percentage to estimate a population percentage. For example, in an election poll, you would select a random sample, and you would ask the people in your sample, which candidate do you plan to vote for? And if 20% of the sample says that they plan to vote for candidate A, then that value of 20% is an estimate of what the population percentage equals. It's an estimate of the percentage of the population that plans to vote for candidate A. So you can, in a lot of studies, you would use a sample percentage to estimate a population percentage. And just like when you use a sample mean to estimate a population mean, when you use a sample percentage to estimate a population percentage, you can calculate these same two values. You can calculate a standard error and a margin of error. The standard error tells you how far the sample percentage is likely to fall from the population percentage. It tells you how far off target it's likely to be. And the margin of error is the distance from the population percentage to the down to this lower boundary and up to this upper boundary. And you would say that there's a 95% chance that the sample percentage fell within this area around the population percentage. So if the sample percentage came out to, let's say, 20%, then what I would say is that, if the sample percentage came out to 20% and the 95% margin of error came out to 5%, then that would mean that this lower boundary is 5% below and this upper boundary is 5% above. And I would say that I had a 95% chance of getting a sample percentage within 5% of the true population percentage. There's one last thing I wanted to cover before the end of this video. In the last few videos, we've been talking about using a sample mean to estimate a population mean. And that can definitely be done in a lot of studies. But in a lot of studies, you actually use... There's one last thing I wanted to mention before the end of this video. In the last few videos, we've been talking about using a sample mean to estimate a population mean. And that's really just one example of using data from a sample to estimate something about a population. It's also possible to calculate a sample percentage to estimate a population percentage. That's what's done in election polls. If I do a survey of a random sample of people, and I ask the people in the sample, which candidate do you plan to vote for? And 20% of them say that they plan to vote for candidate A. That percentage, 20%, is an estimate of the population percentage. It's an estimate of the percentage of the entire population that plans to vote for that candidate. And I would hope that my sample percentage of 20% is somewhere close to the true population percentage, and it's likely to be close as long as I used a fairly large sample size. The larger the sample size, the closer it would be likely to be. Just like how a sample mean is likely to be close to the population mean when the sample size is large. Before the end of this video, I wanted to mention one more thing before the end of this video. In the last few videos, we've been talking about using a sample mean to estimate a population mean. And that's really just one example of using data from a sample to estimate something about a population. In a lot of studies, a sample percentage is calculated to estimate a population percentage. That's what's done in election polls. If I wanted to know what percentage of a population was planning to vote for a certain candidate, I would take a random sample of a certain number of people and ask the people in my sample if they were planning to vote for that candidate. And if, let's say, 20% of my sample say that they plan to vote for that candidate, then that would be an estimate of the percentage of the population. Before the end of this video, I wanted to mention one more thing. In the last two videos, we've been talking about using a sample mean to estimate a population mean. But that's really just one example of using a sample mean. Before the end of this video, I wanted to mention one more thing. In the last few videos, we've been talking about using a sample mean to estimate a population mean. But that's really just one example of using data from a sample to estimate something about a population. In a lot of studies, a sample percentage is calculated, and the sample percentage is used to estimate the population percentage. That's what's done in election polls. If I want to know what percentage of a population is planning to vote for a certain candidate, I could take a random sample of the population and ask the people in my sample if they're planning to vote for that candidate. And if 20%, before the end of this video, I wanted to mention one more thing. In the last few videos, we've been talking about, before the end of this video, I wanted to mention one more thing. In the last few videos, we've been talking about using a sample mean to estimate a population mean. But that's really just one example of using data from a sample to estimate something about a population. In a lot of studies, a sample percentage is calculated, and the sample percentage is used to estimate the population percentage. That's what's done in election polls. If I want to know what percentage of a population is planning to vote for a certain candidate, I could take a random sample of that population and ask the people in my sample if they're planning to vote for that candidate. And each person would give me a yes or a no answer. So each person's answer would be yes or no instead of a number. And then I would calculate the percentage of my sample who said that they plan to vote for that candidate. And then the sample percentage that I've calculated would be an estimate of the percentage of the entire population that plans to vote for that candidate. That would be an example of using a sample percentage to estimate a population percentage. And when you use a sample percentage to estimate a population percentage, you can calculate these same two values, which are the standard error and the margin of error. They have different formulas when you're dealing with percentages, and we actually won't get to those formulas, but the two values really mean the same thing. The standard error tells you how far your sample percentage is likely to be from the population percentage. It tells you how far off target your sample percentage is likely to be. And the margin of error gives you a range around the population percentage in which your sample percentage was likely to fall. So let's say I calculate the sample percentage and it comes out to 20%, which means that 20% of my sample said that they plan to vote for the candidate. Let's also say that the standard error comes out to 3%. So 20% and 3%. What that tells me is that my sample percentage of 20% was likely to be about 3% away from the population percentage. It was likely to be about 3% off target. Now let's say that the margin of error comes out to 5%. So I have a sample percentage of 20% and a margin of error of 5%. What that's telling me is that this lower boundary is 5% below the population percentage, and this upper boundary is 5% above the population percentage. And my sample percentage that I calculated had a 95% chance of falling between those two boundaries. My sample percentage had a 95% chance of falling somewhere between 5% below the population percentage and 5% above the population percentage. So I can be 95% confident that my sample percentage fell somewhere between 5% below and 5% above. In other words, I can be 95% confident that my sample percentage is somewhere within 5% of the true population percentage. And I wanted to talk about how the 95% margin of error is interpreted in an election poll in which the sample percentage is estimating the population percentage. What you actually have to do is you have to take the sample percentage and then add and subtract the margin of error. So this is what you would do if you wanted to find out which candidate was likely to win the election. So let's say my sample percentage comes out to 55%. And the margin of error comes out to 7%. So I have to add and subtract 7%. If I subtract 55 by 7, I get 48. And when I add 55 plus 7, I get 62. So I get these two numbers by adding and subtracting. When you add and subtract the margin of error from the sample percentage, which is the symbol p hat right here, you get these two numbers. You get a lower number and an upper number. If the lower number is below 50%, then you actually can't be confident that the person will win the election, because the margin of error is telling you that the true population percentage could easily be as low as 48%. And if it is that low, then the person isn't ahead. They're not winning. So if this was the outcome, then I just wouldn't know which person was going to win. It would be inconclusive. But if this percentage was a little bit higher, then these two numbers would be 51 and 65, and 50% is below this lower number. So 50% isn't between the two numbers. In this case, I could confidently say that this candidate is ahead, and is ahead in the race, because the sample the population percentage could easily be as low as 51%, and I don't expect it to be any lower than that, which means that I'm confident that the person is ahead. So overall, if you want to get an idea of whether a person is ahead in the election, you take the sample percentage, the percentage of the sample that said that they plan to vote for the election, and you add and subtract the margin of error. If this number, this lower number, is above 50%, like it is here, you can confidently say that the person is ahead. But if that's not true, if this number, lower number, is something below 50%, like 45, then you can't confidently say that they're ahead. It's inconclusive. That's how the margin of error can be used to decide whether a certain candidate is ahead in the population based on data from a sample.